Okay, so today, or in this video at least anyway, because today might be the same day as any other day. Anyway, in this video at least, we're looking at the AS paper 2 from 2019. And if you've seen the video on paper 1, we're basically going to follow the same method through. So we're going to look at each question in turn and maybe consider the types of things to look for when trying to answer these questions, and then we'll also then obviously look at the actual answers. So this first question was all about the organic tests section. So for those of us who went into lockdown before we actually did the tests at school, that meant that we were really relying on a sort of a theoretical prescription. We haven't actually done them. But the principle about how you approach these questions doesn't really change. So we were given 3 different molecules. And what we've got to focus on whenever we're doing a test, it's always focused on the functional group, or at least the type of compound or the homologous series that it features in. So we have a ketone, we have a carboxylic acid, and we have an aldehyde. And then what they've done is they've broken it into 2 questions where we're trying to distinguish between 2 combinations of those compounds. So the first one is A and B. So we're trying to distinguish between a ketone and a carboxylic acid. And the first thing to say is there is no test, or at least as far as AQA is concerned, there is no test that's going to give us, that we can give us a positive observation with a ketone, but there is a test that can give us a positive observation with a carboxylic acid. And the key part there is the fact that it is an acid. So if we add a carbonate base, one that's soluble, we know that a neutralization reaction will take place. We know that carbon dioxide will be produced, and if it's all taking place in a solution, then we're going to see effervescence or fizzing. So that's what we're going to see here. So we're going to add something like sodium carbonate. Now, just before we carry on about the observations, this is a general point, right? So quite often they ask you for a reagent, and by reagent what they mean is what you would take, or what would be the label on the bottle. So with reagents, you have to include the part of the name which maybe isn't actually relevant to the actual reaction. So the sodium, for example, doesn't take any part in this reaction, but we would be using a bottle of sodium carbonate. Now, if you write a formula, that has to be correct. So in many cases, it's often safer to just write the name. So if you had written NaCO3, for example, you would not get the mark for that. You would not get that particular mark. So it's sodium carbonate, and then with the ketone, there would be no change, or there would be no observation. And with the carboxylic acid, we would see effervescence or bubbling or fizzing. And so really that should be an easy 3 marks in the long run. Okay, I appreciate at the moment you're still getting used to the idea of organic tests, but in the long run that should be an easy mark. And part of the strategy is perhaps writing or noting or making it really clear to yourself which homologous series these molecules or what the functional groups are. So we look at A and C. A is ketone and C is an aldehyde. So this is a more standard comparison. So often when they introduce the tests of aldehyde, it is in comparison with a ketone. You're trying to distinguish between these 2 products from the oxidation of alcohols. And so there are a couple of answers, or a couple of reagents that you could use. I'm just going to go for Tollen's reagent. It could be Fehling's reagent, but I'll talk about that separately in a second. So go for Tollen's reagent, and again with the ketone there's no change, and the observation with a aldehyde or with an aldehyde is that there's a silver mirror formed, or they might allow black precipitate as well. Actually, we could have used Fehling's reagent. We still would have had no observation with the ketone, and we would have had a red precipitate formed with the aldehyde. Essentially, what's happening here is whatever reagent we're doing, the reagent is being reduced, or part of something in the reagent is being reduced, because a key difference between an aldehyde and a ketone is the fact that an aldehyde can be oxidized further, whereas a ketone can't. And so if the aldehyde is oxidized, then something else must be reduced. And in the Tollen's reagent, there are Ag+ ions, and they are reduced to, they each gain electrons, so they reduce to form silver metal, and that's why we get the silver mirror formed. And in the case of failings, we've got copper 2+ ions, so the failing solution is blue, but that's reduced to form a red precipitate where the copper is a 1+, has an oxidation or charge of 1+, and so we've got the reduction. So there's a redox reaction essentially going on in the positive results with the reagents like Tollens reagent and failings. So here we've got bromoethane with potassium cyanide, so it's a nucleophilic substitution, so we should see, quite quickly that that's a haloalkane, and haloalkanes undergo nucleophilic substitution. It asks us to outline a mechanism. It's only 2 marks. And so there's our nucleophile. So in terms of what the 2 marks are for, things that could lose you a mark is not having the charge on the cyanide because it is an ion. You absolutely must have the lone pair of electrons and the arrow starting from the lone pair of electrons. So remember, an arrow like this always shows the movement of a pair of electrons. And so an arrow can only ever be from a lone pair, which you must show, or, as we've got in the second arrow, from a bond, because that is the movement of that pair of electrons that are being currently shared between the carbon and the bromine. So that is 1 mark, if you like, and the second arrow is the second mark. And then it asks us to give us the UPAC name of the product. I seem to have cut off the product part of it, but anyway, give us the UPAC name. In a sense, nitriles feature really, or we look more closely at nitriles in the aldehydes and ketones section, perhaps, of the post-AS content, although, there's nothing to say we couldn't have looked at the naming of nitriles. But key things to just point out, it will be all one word, right? So you can't have a space. You don't need to number it because the nitrile will, by definition, become the first, or the carbon in the nitrile will become the first carbon in the numbering system, so you don't need to number it. But what some people miss out is the E here. And I understand that, because if we were talking about ethanol, for example, we are not calling it ethanol. But I think, I don't know, this is the convention. It's probably because otherwise it would be 2 N's like that, but it's very clearly the full alkane name here and then followed by nitrile. Okay, and now we're being asked to calculate the percentage atom economy for this reaction. So the thing that we want, the substance that we want, is compound D, which is the propane nitrile. But we've got to look at the atom economy for this reaction. Oh yeah, sorry about that. So I keep forgetting what I've added to this. So atom economy is the useful product. So the total mass of the useful product divided by the total mass of all of the products. And so what we're doing is we're adding up the MRs, but also if there was 2 of them or whatever. So we can see that the yellow is just the propane nitrile, whereas the total product is the propane nitrile plus the potassium bromide. So we have to look at our periodic table to work this out, or to start this calculation. So 55 over 174 times 100%, and we get 31.6%. So it's not a difficult calculation. It's just, I guess, where you can go wrong is you can forget how to do atom economy. But there is a fair chance that an atom economy question is going to appear in an exam in one of the papers at some point. So it's not marks really you want to lose. It's not marks you don't want to get. So this was an unusual or an atypical question to do with enthalpy of combustion and the whole Q equals MC delta T area of the course. So how to approach this? How the best way to approach this? Well, I think quite quickly you can recognise the part of the course that's relevant to it, like that it was energetics, and that you did a number of different types of calculations in energetics, but you have a fair idea of which one is relevant here, specifically because, or especially because, they give you a specific heat capacity of water. So I think your best place to start, and again, if we're thinking about strategies, is to write the equations that you know to be relevant to calculations of this nature. So Q equals mc delta T, where Q is energy transferred, and that energy could be being released or taken in. That doesn't matter. It's a transfer of energy. Mass, now it's whatever is changing temperature. Okay, that's very important. So it's the mass of whatever is actually changing temperature, and you know the thing that's changing temperature is in effect defined by the specific heat capacity, and that's of water. So it's going to be the mass of water, the specific heat capacity, and the change in temperature. So capital D is a big change. It's delta, right? Delta T. And then the other equation that is also relevant is the enthalpy change, or the enthalpy change of combustion here, equals the energy transfer divided by the moles that led to that energy transfer. And if we look at one of the values that were given, we have been given delta HC, right? So we have got a value here. Now, typically, most of the questions that you've ever done, you've been working from here, from the first equation, all the way through with the result or the aim of determining delta HC. This is different. In this time, they want us to calculate the final temperature. But if we're to calculate the final temperature, what we actually have to calculate is the temperature change. So in this example, we're going to be working backwards, right? So we have like what we typically think of as the end, and we've got to work back to something that we normally expect to get at the beginning. So then we've got to think about, well, I've got to do something with this expression first. And so what can I do? Now, the energy transfer Q is what you're going to try and work out here, because it's the moles that you're going to be able to use the information here to determine. So you've been given, and this is something, again, that you have to be aware of, and it's the sort of thing, actually, this particular use of a table is not uncommon, right? So this type of question where you're trying to get the final temperature is maybe rare, but the use of something, a table like this, and this sort of information is not uncommon. So we can see there are two masses, an initial mass of the spirit burner and cyclohexane, and the final mass. And so the spirit burner doesn't change, but clearly what's changing, what's leading to this difference, is the cyclohexane. And that's what's reacting, that's what's combusting. So the change in mass is telling us the mass of the cyclohexane that reacted, and from that we were able to deduce, or we know that the enthalpy of combustion per mole is this value here. So let's work out what that mass is. So it's 0.63 grams, and if we have a mass and we have a formula, they're very kindly given us the formula of cyclohexane up at the top, then we can work out moles. So our moles is going to be our mass divided by our MR. So now we have how many moles of cyclohexane was combusted. And we know that the enthalpy change per mole is minus 1216. So we can rearrange, sorry, that's a repeat of the question. Now the plus or minus is because it's only at the end that we decide whether to put the minus or the plus. That's due to whether the temperature has risen or decreased. But as far as Q is concerned, Q isn't plus or minus, right? Q is just energy transferred. So we can actually ignore the fact now that it says minus 1216. So we can rearrange the equation so that in terms of Q, because that's what we need, because that we need to do the next bit. So the enthalpy change times the moles, because we've times both sides by moles, equals the energy transferred. So, and look, I've dropped the minus because the minus was just there because it was exothermic, but all I'm focusing on is the energy transfer, so I don't need that. That's just a confusing thing and could actually affect our final answer. So it's 7.5 times 10 to the minus 3 moles times the enthalpy of combustion. We get it in kilojoules because our enthalpy of combustion was in kilojoules, but we're going to need it in joules because if we look at our specific heat capacity, that's the unit the specific heat capacity works with. So again, I think you can see you're working backwards. In the questions you've done many times before, you would have got Q, and you could have got Q as 9,120, but when you came to do the next bit to work out the enthalpy change, you would have divided that Q by 1,000 to turn it into kilojoules. Okay, so we're now moving on to Q equals MC delta T. Well, we know what Q is, but anyway, what we know what M is and we know what C is. So we're going to rearrange the equations so that delta T is our subject. And I think I know I stated this in the video on the paper one. Please, before you start doing anything with numbers, the thing that you're trying to find, make that the subject, so that you can just simply plug the numbers in. Don't plug the numbers in here and start rearranging it, because you are much more likely to make a mistake. So just put our numbers in, right? So you could be doing this straight into your calculator. So there's our energy transfer that we worked out. There was 50 grams of water. It's got a specific heat capacity of 4.18. And so we get a temperature change. And of course, the temperature change, technically, if we look at the units of specific heat capacity, is Kelvin. But a temperature change in Kelvin is also a temperature change in degrees Celsius. So a change of 1 degree is a change of 1 Kelvin. So the scales match up, except they just start in different places. But a 1 Kelvin, 1 degree Celsius change is the same. So we know what it's changed by. So we go back to what the initial temperature was, which was 19.1. That was one of the pieces of information in the table. And we then say, right, well, it started at 19.1. It's changed by 43.64. The fact it was exothermic meant that the energy was being released and therefore the temperature was going to rise. So we are adding our 43.64 to our 19.1 and we get a final temperature of 62.7 degrees. And then this is such a bog standard question, isn't it? So we have a data book value which is much greater than the value that we have, or the value that the experiment determined, and we have to explain that difference, and it's just, I mean, this is the simplest answer: heat loss to the surroundings. So not all of the energy that was released in the reaction actually went into heating the water up. Some of it, the fact that it's, we can see there's light, there's an energy transfer, clearly not going exclusively directly into the vessel that the water's in. Another possibility, or something they would have accepted, is the fact that some of the cyclohexane could have evaporated, and so we appear to use the change in mass was greater than what it actually was, because some of it was through combustion. So maybe the mass change might have been a gram, but actually only 0.9 grams was the mass of cyclohexane that actually reacted, and 0.1 grams was lost through evaporation, because it's quite a volatile substance. But heat loss to the surroundings is a very standard answer. Here we've got essentially a Hess cycle, right? So we're given enthalpies of combustion for carbon, hydrogen, and cyclohexane. And if we're combusting something, then whatever we're combusting is reacting with oxygen, so the arrow is leading away. So anything that's combusted, the arrow leads away from whatever is combusted. So we just put the values in. We've got to realise that we've got, in terms of the stoichiometry, we've got 6 carbons, 6 hydrogen, or 6 hydrogen molecules. So we've got to do, because these are per mole, we're saying 6 moles, 6 moles, and 1 mole. Our dotted arrow here is to say, well, this is what we're trying to work out, the question mark. So we want to go from the left-hand side of the equation to the right. We can't. We're trying to determine it, but Hess' law says the energy change is independent of the route taken. So we take a different route, and then we are going with these arrows. So we keep the signs as they are, and we're going against that arrow. So we change or reverse the sign. Oops, sorry. And so you can see that's become plus 3920, and so we get our answer of minus 160. Okay, so there's not a lot to say about this. If it's complete combustion, you've got to recognise that an alkane produces carbon dioxide and water, and then you've got 6 carbons, so you've got to make 6 carbon dioxides, and then you've got 18 hydrogens, so you've got to make 9 waters, and then you've just got to balance it from there. You can have multiples. You could have had 2C8, H18, 25O2, etc. But I mean, it's fine to do. It's certainly acceptable to do half values when oxygen is involved, or if it was something like a definition, like a enthalpy of formation or something. And then there were actually a couple of options for the next question, but I'm just going to give you one. And you know, just this is probably something you just have to. This is just a recall or memory fact. You could possibly work it out from first principles, but anyway, it's not a big deal. It's not something for me to spend a lot of time talking about. This was generally well answered, but again, you know, there were people who made mistakes, and they probably made mistakes for reasons that didn't need to happen. So I think sometimes people jump too quickly into the question. I think you want to try and get the information into the form already for you to use, rather than just diving into using it. So we were told it's 6.49 million tons. So let's write that as a number, and then we know that our answer has to be in kilograms. So we've got to turn tons into kilograms, and so there are 1,000 kilograms in a ton. So that's how many kilograms we've got. And then you could have worked out then how many moles, but you can also do it as a ratio. So the ratio of calcium oxide to sulfur dioxide. So 6.49 million tons was the mass of sulfur dioxide. We could have worked out how many moles that was, and then, you know, it would have been a 1-to-1 ratio with the calcium oxide, and then we could have multiplied it by the MR of calcium oxide. But you can do it this way. It's the same. You get the same answer. So there's our answer. We have to give it in standard form. We've been given the values that we've been given are to 3 significant figures. So we should be writing our standard form to 3 significant figures. This is also I want to say it's a classic question. It's a question that shouldn't be a surprise, or at least you should be ready for this sort of question. So it says, draw a diagram to show how 2 methanol molecules interact with each other through hydrogen bonding in the liquid phase. And there are 3 marks. And I think a lot of you understood the principle, but you certainly didn't understand how to get the 3 marks. So obviously we're going to draw a methanol first. Now, to be honest, well, I would not saying I would definitely get 2 marks just for drawing this, because that's not showing any sort of interaction. But what I've drawn already features, or has features for 2 of the marks. The lone pairs are very important, because a hydrogen bond is between a delta positive hydrogen that's bonded to an oxygen and a lone pair of electrons. Okay, that's really important. And that lone pair could be on a fluorine, nitrogen, or oxygen. So in terms of where the marks came here, they were very clear that they wanted a delta plus and a delta minus on the same OH. Okay, and now I would just get into the habit of just doing it full stop, all right, and do it on both of them. They wanted to see that you would recognize there were 2 lone pairs, and then of course there's the interaction. So most people did get this mark, which was showing the hydrogen bond. But you needed to have it clearly from a delta positive H to a lone pair, and you needed to show both the lone pairs, and you needed to make it clear that the OH bond was delta minus delta positive. That really shouldn't be a surprise. Okay, you should be ready for a question like that to get 3 marks. Bond angle around the oxygen atom in methanol is slightly smaller than the regular tetrahedral angle of 109.5. Explain why this bond angle is smaller than 109.5. So some of you just wrote because lone pairs repel more. More than what? Right? So you've got to make it. If you're going to say something is more than, or greater, or weaker, or stronger, you've got to say compared to, and you have to say what it's compared to. And so. Or you said, some people said lone pairs repel. Well, yeah, but so do bonding pairs. So you've got to mention both. So lone pairs repel more than bonding pairs. That is why the angle reduces, because the angle is the angle between the bonding pairs. So you've basically squeezed the bonding pairs slightly closer together. Okay, so that again, a question to be ready for in the future now that you see that this is how to answer it in an exam. So this was interesting. So a lot of people got good marks, got high marks, but you spent an inordinate amount of time writing stuff that just wasn't necessary. And I think that comes down to a couple of things. It comes down to confidence. And I understand why you feel the need sometimes to make sure you're getting everything down. But it's also about confidence and awareness of the command words. This does not say explain. Other questions that we've seen, or we saw in paper one, there was one where we had to explain the change in ionization energy across period 2. This one is a describe. Okay. Then the other thing that was a bit iffy with some of you is that you were talking about this pressure and you were talking about this temperature. But that's not what the question's asking. The question's asking what happens if you change the pressure and you change the temperature. The fact that the pressure is high, low, whatever, is not relevant. What's relevant is what happens if you increase it or decrease it. What happens if you increase the pressure or decrease the pressure. And then the other place that some people got lost a mark or two on is that we've got to talk about catalyst, changing pressure, changing temperature. And when we talk about all three of those, we've got to refer to the equilibrium yield, the reaction rate, and the cost. So we have really 9 points to make, right? We've got 3 under catalyst. So we've got to say what happens to the equilibrium yield, reaction rate, and cost. We've got to say 3 to do with changing the pressure and 3 to do with changing temperature. Okay. So just treat them separately, right? Just take them one by one. A lot of you got into quite convoluted language. It was partly because you were trying to explain things. So simply using a catalyst. So a catalyst has no impact on the equilibrium yield. And I could say because it speeds up the forward and backward reactions equally, but I'm not having to explain it. They do speed up the rate of reaction, and they would lower the cost. If we look at changing pressure, I've got to decide, it doesn't matter whether I say it's increasing or decreasing, I then just have to say what the consequence of that is. So increasing pressure would increase the rate of reaction, and in this reaction, and so we do have to we are thinking of this reaction in our heads, it would give a higher equilibrium yield. But I don't have to explain why. I mean, it's good that you did, and because that's the side with the fewer moles, and increase in pressure shifts the equilibrium to the side with the fewer moles, but we didn't have to do that. We just have to say what happens to the equilibrium yield. Because in a sense, knowing that the equilibrium yield of the methanol increases requires us to understand what increasing the pressure does. Okay, so that's fine. And then a higher pressure, of course, that would mean higher costs. So pressure is always a very expensive, particularly in industry. And then changing the temperature, again, I'm just going to go with increasing. Doesn't matter whether I go with increasing or decreasing, as long as I say that the effects are. So increasing the temperature increases the rate of reaction. However, doing so reduces the equilibrium yield, because in this particular one, it's exothermic going forward, and increasing temperature favors the endothermic direction, so it's going to shift to the left. And of course, increasing temperature increases costs. And all I've got there is 6 marks, and 6 very strong marks. There's no, ooh, should I give them that final mark or anything? That's going to get me the 6 marks, no problem. This was generally pretty well done. I mean, they were quite nice. They were telling you what you were ending up with, and they told you it was propene, so you knew what to start with. And the fact it's an alkene means it's going to have to be an electrophilic addition, because you're clearly adding something. And so this is the first part. So there's 5 marks, and I'll explain where the 5 marks. So obviously one has come from saying electrophilic addition, and then remember it's the electrons in the pi bond that are the ones that move. This would be a delta positive hydrogen, a delta minus oxygen. So we have a movement to form a bond with a hydrogen, and then the electrons between the hydrogen and oxygen in that bond move on to the oxygen. So we get a carbocation intermediate. So second mark is this arrow, third mark is this arrow, and the fourth mark is that you've drawn the correct carbocation. So it has to be 1 that's going to give us this product. And then this was a place where I guess you could lose a mark. You needed to make sure that you had a lone pair of electrons on your oxygen, and that's where the arrow was coming from. So that lone pair of electrons there represents this pair shown, or the movement, or shows the electrons that have moved in this arrow. Of course, there would be 2 more lone pairs, but you only have to show the one that, or show 1, because that's what's going to form the bond with the carbon. And I'm afraid you also have to remember to include the minus sign, because that oxygen now has 1 more electron than protons, so it's going to have a minus charge. And you don't have to put the product because they've given you the product, but what I would tend to say is why not, right? Because it gives you confidence and faith in what you're doing. You can see that, yes, that is the consequence. That is what I would have produced from that, and that is what they have at the top there. Next question, it says draw the structure of F. So they said we formed 2 isomers, and they gave us E, which was one of the isomers, and we did the mechanism to produce that. So the only other possibility is that the hydrogen sulfate is at the end of a chain, so we just have to make sure it's on the first carbon, right? It doesn't matter which end we count from, it could be on the right hand end, but it's the first carbon. And then explain why more of isomer E than isomer F is formed. Now, a lot of you had a sort of a general idea, had a vague idea. You knew it was to do with carbocations, and you knew that it was to do, or many of you knew it was to do with stability, but your phrasing suggested that you weren't totally secure in really understanding it. So some of you were saying isomer E is a secondary carbocation. No, it's not. That is not a carbocation. There is no carbon with a positive charge on it. The word that you want to use to make sure that you're giving a stronger answer is via. It's formed via. So it's like I'm going from one station to my final destination, but I'm going via this station. So if I just go back, this is my starting point, this is where I end up, but I have gone via this carbocation. And so we're going via a secondary carbocation, and that secondary carbocation is more stable than the primary carbocation that F is formed via. So again, if you're saying more stable, you've got to make it clear what you're comparing it with. You can't just say it's more stable. You can't even just say it's more stable than a primary carbocation, because, well, yes, so what? You've got to make it clear that it's more stable than the primary carbocation that F would have been formed via. Okay? So, yeah, so that's the general rule there. Okay. All right, so propandioic acid contains 2 carboxylic acid groups, so they've spelt that out. It's a solid organic acid that is soluble in water. Okay, so it says draw the skeletal formula of it. And if you think about what a carboxylic acid group looks like, they both have to be at the end of our 3-carbon chain. So our skeletal formula is going to look like this. Now, where a lot of people lost marks is that, for example, here they might have written OH, and just like it's written here. But the thing is, that is incorrect, because that implied that the bond was to the hydrogen, and it isn't. And you've got to be so careful about that. So you know that it's the oxygen that is bonded to this carbon here, and so you have to make that absolutely clear when you draw your skeletal formula. And then it asked us to describe how to prepare 250 centimeters cubed of an aqueous standard solution. And a lot of you did great on this, but some of you were clearly stumped. Now, this standard solution here was the first core practical that you did, and you did it for a few weeks as well. So it really should be a question that, well, you can definitely prepare for it, and it shouldn't come out of the blue. It was the first core practical you did, and you've just got to explain how to make a standard solution, basically. So you could use a weighing boat or a sample bottle, right? It doesn't matter. The point is that the steps you then do with it are the important thing. So for this example, it's with a sample bottle, but I'll refer to a weighing boat in a second. So you've basically taken your solid, you've weighed it, or then you've transferred the solid to a beaker, or it could be a flask, and then you've reweighed the sample bottle. And so the difference in those, in the first and second mass, means it tells you how much propanedioic acid you've transferred. And it is very, very, very important to have a very accurate measure of how much of something you're adding when you're making a standard solution, because the reason it's called a standard solution is because it's going to be something that you have faith in and that you're going to compare the concentration of other substances to. It's acting as a standard, right? So we could have done a weighing boat. So the weighing boats could have been used to measure the mass on, and then when we added it to the beaker, what we would have done is we would have washed, or repeatedly, we would have washed the weighing boat to ensure that all of the solid was transferred. So we didn't need to do, with a weighing boat, we don't need to do a second weighing, a second mass measurement, but we would need to do washings to ensure that everything on the weighing boat got into the beaker. And then once it's in the beaker, you're going to add some distilled water and you're going to stir it. But the point is, you've got to get the solid to dissolve, right? So you stir it until it's dissolved, and then you transfer what's in the beaker to your volumetric flask. And so it doesn't tell you a volumetric flask here, but you have to recognize that's what you're going to use. And then you would do repeated washings of the beaker. So you would keep rinsing the beaker to ensure that all of the propanedioic acid is transferred to the volumetric flask. And then you would wash the funnel that you used as well. So you'd just pour water through the funnel, and then you would make it up to the 250 centimeter cubed mark. So you would do it. So, you'd make it up to the mark on the volumetric flask. And then the final thing that you would do is that you would shake or invert the flask to ensure that the solution is thoroughly mixed. Because if you think about when you make a squash, if you use perhaps very cold water, or the squash is very cold or something, it doesn't always mix very well. So anyway, that's why you're shaking it, to ensure that it's all thoroughly mixed. And that, really, honestly, that is an easy 6 marks. That's something that you can absolutely prepare for in an exam. And then it asks us to calculate the mass in milligrams of propanedioic acid needed to prepare, and they give us a concentration and a volume. So concentration is moles over volume, but we have to remember that volume is measured in decimeters cubed. They gave it to us in centimeters cubed. This is a standard thing they do. So you need to convert it to decimeters cubed. We can rearrange that equation. So rearrange it because we know volume and we know concentration. So we can change it to moles. So that's how many moles we've got. And then we're wanting to work out mass, and mass is moles times MR. And they've given us the MR. So we just plug the numbers in, get it in. Don't forget our answer is in grams. They've asked us for an answer in milligrams. So remember how to convert from one to the other. So we're going to multiply that by 1,000, and we get our 130 milligrams. And there's our mass of propanedioic acid. This was an interesting question. So we are given information about propan 1-ol, and they are asking us for the volume of potassium dichromate needed. So when we look at our reaction equation, we are going to need to consider our molar ratios. So just to make them spell them out to myself, I've written them. The other thing that's a little bit stranger is the fact that we've got density, and we've got a volume, and we've got MR. So we know we're going to have mass if we're going to work out moles. So, the useful thing is, by giving us the units of density, they've given us the equation, because they've told us that density is mass over volume. So we need to rearrange that because we're trying to work out mass. We have been given density and we have been given volume. So we plug those numbers in. So we get our mass of propan 1-ol. We are given the MR. All right, so the mass of propan 1-ol is the mass divided by MR. So it's that 4.8 we've worked out divided by 60. So we get the number of moles. So we have used up 3 of the values that we've been given so far. So remember, I think I mentioned this in paper 1, if you're given a number, you will absolutely have to use it. So if at the end of the question you've failed to use a number that they've given in the information, you've definitely made a mistake. Anyway, so we've got the moles of propan-1-ol, and there is a molar ratio of propan-1-ol to dichromate, and it's a 3-to-1 ratio. So that means we need a third as many moles of the potassium dichromate. So now we've got the moles of potassium dichromate. We've got moles now of dichromate. We've got concentration, so we can work out volume. Volume is moles divided by concentration. Plug it all through, and we end up with our 67 centimeters cubed. Okay. Right, so this was an unfortunate question for you, given that you hadn't been able to do the practical before lockdown. So it was a mean. Well, I mean, it's the question in the exam, but it was something that you were going to find more tricky. So the thing is that we have got propanal and we've got propan-1-ol, and there is a difference in the intermolecular forces present. And propanal is an aldehyde, so it only has dipole-dipole, whereas the alcohol has hydrogen bonding. So what that tells us is that the boiling point of propan-1-ol is going to be higher than the boiling point of propanal. It could be the case that the propanal got oxidized further to carboxylic acid, but the carboxylic acid would also have hydrogen bonding, so the carboxylic acid would also have a higher boiling point than the aldehyde. So we want to basically extract the aldehyde as it's made, and we can do that because it's got a lower boiling point. So we're going to use a distillation apparatus. So I'll explain its features in a second, but this is where the reaction is taking place. The vapor is going to travel up. Your thermometer should be at the opening of, this is going to prove to be the condenser, but it's got to be at the opening because we want to measure the temperature of the vapor that is about to go down the condenser, because that's going to give us some information that we are distilling off what we hope to or what we want, because we can see essentially it's going to give us essentially the boiling point of that substance. In terms of drawing it, you have got to make it clear where things are open and where things are closed. And so we need this bit here to be open because we need the vapor to be clearly possible that it's going to travel this direction. But we do need this bit at the top closed because we don't want to lose vapor by it just sort of basically coming out of the top here. So we needed to show a condenser. It needed to look like a distillation apparatus. All right, so you could get 1 mark if it just vaguely looked like a distillation apparatus, but it needed to be clear that the substance could travel all the way from, the vapor could travel all the way from the pear-shaped flask all the way to what we were collecting it in. This shouldn't be sealed right at the end because we need a way for the pressure to be released. This would not be open here because we want to make sure that the vapors travels along. So we just got to not have it completely sealed here. And then the final mark is you had to make sure that the water was going in at the bottom and coming out at the top. So that's really where the 3 marks came. So this is about free radicals, or it's about free radicals really, and they give us a CFC, and they ask us to give an equation for the breakdown of 1 molecule to form 1 chlorine radical and 1 other species. So when they use that word species, they're doing it so that they don't give you any unnecessary clues as far as they're concerned. And actually a lot of you fell for it. So if they'd said 1 chlorine free radical and another radical, a lot of you, more of you would have got it right, but a lot of you drew a second species that wasn't a radical, and yet it has to be. We are essentially, this is an initiation reaction. So there's our chlorofluorocarbon. We're saying that there's a chlorine radical formed, so it must be one of these chlorines that's stripped off. And that leaves behind, if it's a free radical, that means only one of the electrons in this covalent bond goes off with the chlorine. So the radical must be left behind. And it must be on that carbon, and you really should make that clear too. So if you have got no radical on the left and a radical on the right, then there must be a second radical. Okay. And then it asks for two equations to show how chlorine radicals catalyze the decomposition of ozone. So this is a bog standard set of equations, absolutely something that you can learn. This is not an application of knowledge. So you start with chlorine free radical, and it's reacting with ozone. It makes a chlorate free radical and O2. And then whatever free radical, this is a propagation step, so whatever free radical you have formed in the first step of the propagation has to appear on the second. Oh, I've made a little mistake there, haven't I? Apologies. Let me just make that slight correction. That should be A3. Sorry about that. Okay. And if we added those two equations together, the chlorate free radical and the chlorine free radical would disappear, and we'd have 2O3 goes to 3O2, and that is a decomposition reaction. What have we got here? So butane can be used as a replacement for CFCs in refrigerators. During its use, the butane is repeatedly converted from liquid to gas and then back to liquid. This is actually how the refrigerators work. This is how they draw heat away from or energy away from the inside of the fridge. So the liquid butane expands as it turns into gas. So you've got to show you're working. So we've got different things we've got to work out. So the first thing we've got to do is they've given us R, they've given us pressure, they've given us temperature. We're going to be using PV equals nRT. And what they're asking us to work out anyway is calculate the volume of gas. So there's always a PV equals nRT question somewhere in the exams. Now they're asking us to work out the volume, so we need to rearrange that equation to have volume as the subject. And believe it or not, well, not believe it or not, but that is the first mark. So you should write this out, not only because it's going to make it less likely you're going to make a mistake, but secondly, because it is a mark. So if you do make a mistake on the next bit, you've at least got that mark. N is number of moles. So we were given a mass of butane. They gave us the MR, so we can work out the number of moles of butane. We've got to just realise that when we're doing the calculation, pressure is in pascals, not kilopascals, so we have to change that into pascals. And then we're simply putting the numbers in. So there's the number of moles we calculated. There's the R that they gave us. There's the temperature in Kelvin, which they gave us. And there is the pressure. So that gives us a volume. But we've got to remember that this volume, according to this equation, the units of volume are meters cubed. And so meters cubed to decimeters cubed to centimeters cubed, these are the conversions. If you're not sure if it's a meter cubed, what is a meter cubed? It's 100 centimeters by 100 centimeters by 100 centimeters. So it's 1,000,000 centimeters cubed. So we're going to multiply our meters cubed by 1,000,000, and we get our centimeters cubed. And that's 4 marks. So getting to this point here is 4 marks. Then the volume of liquid butane, they gave us density, so another one of those densities, but we just had to rearrange densities, mass over volume, so we get it in, so that volume is the subject, put the numbers in, they gave us the mass, gave us the density, so we get the volume. And then the expansion factor is simply the volume of gas over the volume of liquid. So 15,000 over 64.7, which is 232. So it expands by a factor of 232 times. Okay, so we're being asked about concentration in moles per decimeter cubed of ethanol if we had 80 milligrams of ethanol in our 100 centimeters cubed of blood. So milligrams, we're never using milligrams in chemistry, so we're going to convert that to grams. And we know when its concentration it's decimeters cubed, so we're going to turn the 100 centimeters cubed into decimeters cubed. So from the mass we can work out the moles of ethanol. So we now know how many moles there can be or there are in the 100 centimeters cubed of blood. Concentration is moles divided by volume in decimeters cubed. So there's the moles that we've calculated divided by the volume. So we get a concentration, and we can see clearly that that is C. There is just an example sort of distribution. So it says the curve is symmetrical about the maximum. Well, no, it clearly isn't. There is no line of symmetry through the maximum. There are always some molecules with zero energy. No, it's very important when you draw your graph that it starts at the origin. So there are no molecules with zero energy. The position of the maximum of the curve is not dependent on temperature. Yes, it is. So the one in grey is at a higher temperature. So the position of that maximum is now different to the one that is orange, which is at a lower temperature. And then the mean energy of the molecules is greater than most of the probable energy. So most probable energy is wherever the peak is highest, but mean is going to be slightly to the right because it's the average of all of the particles. And if we look at where the maximum is, there are still more particles to the right of that than there are to the left. So, and that becomes from the fact it's not symmetrical. So the mean energy of the molecules is greater than the most probable energy. The mean energy would be somewhere like here, whereas the maximum is there. When 1 mole of ammonia is heated to give a temperature, 50% of it dissociates and the following equilibrium is established. So what is the total amount in moles of gas in this equilibrium mixture? So the before is we've just got the 1 mole of ammonia and obviously 0 of nitrogen and 0 of hydrogen. And it says 50% of it dissociates. So that means half of it is used up. So we've got half left over. And then we look at the molar ratio. So the change is a half. So that means nitrogen has increased from 0 to a quarter. And hydrogen is increased from 0 to 3/4. And then when you add all of those up, you get 1.5. Which compound is not an isomer of the following compounds? So again, if you want to make this easy for yourself, draw the hydrogens on, right? Just draw the hydrogens on, and then just work out what that molecular formula is, and then just work out the molecular formula of all of the compounds listed here, and you'll see that it has to be D. D is not an isomer. It does not have the same molecular formula as our compound that we're given there. I think this was a really unfair question, I have to say. And the reason is because the possible isomers include things, something called amines, and you have not done amines. They are a year 13 or they're a post-AS topic. And, you know, whilst, okay, this is about isomers, and by the end of the final exam, we could be asked about isomers on to do with any of the topic areas that we've done, any of the homologous series. I just feel it's not, it wasn't fair on you, this particular one. So well done to you if you got it right, and don't worry if you didn't. But these are all the possible, these are all the possibilities that you could have got. These are all actually amines, but the difference is, and something we haven't done, is that this is a primary amine. This is also a primary amine, and then we've got a secondary and we've got a tertiary amine. So, like I say, don't worry about it, but they would all have that molecular formula. Ask us about which one represents a propagation step. So the fact that we've got two radicals coming together, that must be termination, and that's the same for the B as well. The fact that we are going from a molecule to two radicals means it must be initiation. Propagation is where we have molecule radical. We have one of each on both sides of the equation, so it must be D. Which compound can react with ammonia to produce propylamine? So the point is, you might, again, propylamine might not be something that you recognize, but the fact is ammonia is a nucleophile, and the only time you've used ammonia in the organic chemistry was as a nucleophile. So it must be something that can undergo nucleophilic something or other, right? And again, I've done a mistake here actually, so just going to put that through. That should be nucleophilic substitution. Whoops. Anyway, sorry about that. But anyway, alkenes undergo electrophilic addition. Alcohols undergo elimination or oxidation. Haloalkanes or halogenalkanes undergo nucleophilic substitution, and alkanes free radical substitution. So given that ammonia is a nucleophile, it's going to be the haloalkane, it's going to be C. Which statement is not correct? Well, Well, let's just work from the bottom, actually. So it's got a carbon-carbon double bond, so of course it's going to decolorize bromine water. It reacts with electrophiles. Well, that's what electrophilic addition means. So when you get the name, like electrophilic addition, that electrophilic bit or the nucleophilic bit is referring to the species that your homologous series or your functional group is reacting with. So your carbon-carbon double bond or your alkene is reacting with an electrophile. It forms an addition polymer. Yeah, absolutely. That's how addition polymers work. They are formed from alkenes, and then displays EZ isomerism. Now, if we look at where the carbon-carbon double bond is, it's at the end of the chain. We've got two hydrogens attached to one of the carbons. Therefore, we cannot have EZ isomerism. Which compound can be oxidized to form, and then it's given us a ketone. So the key to here is to draw the ketone and then to think, what would I have formed that from? So you're working backwards. And to make a ketone, you use a secondary alcohol. So if you drew the skeletal diagram of the thing that's made and then just drew a skeletal diagram for the alcohol that would have produced it, and then you name it, that's how you could go about trying to work out what the actual answer is. So draw, I think, skeletal formulae. It's very rare that you get questions specifically about skeletal formulae, but I think they are really useful. It's a really useful thing for working stuff out, and that's why I feel it's absolutely in your interest to practice and be comfortable with skeletal formulae, because it makes answering questions like this, I think, a lot easier. So that was the product. We drew a skeletal formula of what we would have made, what the product would have been made from, and then once you've got that, you can just do your normal nomenclature method. Which species can act as a nucleophile? So the whole point about a nucleophile is it's an electron per donor. So if we just think of the structures, there's only one of them with lone pairs of electrons, and that is the methanol. So I've drawn the structures of the other, but you can very clearly see that obviously oxygen has got two lone pairs on it. And so that's a very straightforward question once you realise that. Which alcohol forms a mixture of alkenes when dehydrated? So the thing about alcohols, or propane 1 or propane 2-ol, is they are going to mean the same thing. Propene can only exist in one form. There's only, with the 3 carbons, you can only have a carbon-carbon double bond on the first and second carbon. Pentan 1-ol, because the OH is at the end, the hydrogen that would get removed must be from the adjacent carbon. That's the only place it can be, so we can only get one product. But with pentan 2-ol, it's different, because we could have a hydrogen taken from here, or we could have a hydrogen taken from here when the dehydration took place. So we would get 2 possibilities. We could have the carbon-carbon double bond at the end, or the carbon-carbon double bond on the second carbon. So that is a mixture that gives us 2 position isomers of each other. And actually, it would also give us 3 products, because this one here would display EZ isomerism as well. So we'd actually get 3 products there. Which of these compounds, these are all organic compounds, which of these compounds has the highest boiling point? So, I mean, they don't all have the same MR, but they're 3 carbon chains. So what they're trying to say is that they're not really considering the size of the molecule to be a factor. So really we're looking at which one of them has the strongest intermolecular force. So haloalkanes have permanent dipoles, or dipole-dipole forces, and the first 2 are both haloalkanes. And yes, there would be a difference in their intermolecular force, but we'll still stick with the fact they're just permanent dipoles at the moment. The same with an aldehyde. But crucially, a carboxylic acid has hydrogen bonding, and instantly that elevates it. And that is a stronger intermolecular force than permanent dipole-dipole. So it would be our carboxylic acid that had the highest boiling point. Okay, so it says, which compound cannot be produced by reacting 2-bromo-3-methylbutane with sodium hydroxide? So again, using my skeletal formulae, draw 2-bromo-3-methylbutane. The fact is, haloalkane means it can undergo either elimination or nucleophilic substitution. So I've got to think about what are the possible products of those reactions. I could get two possible products with elimination. I could get one possible product with nucleophilic substitution. Which one isn't one of the ones listed? Well, I didn't actually do it, did I? But it's the 2-methyl-butanene. Because if you look at the numbering and you look at the skeletal formula, you can see how the names correspond. A lot of you got this wrong. So it's important that we appreciate this. Now, I know it's not giving us a massively accurate reading number here, but it's quite a way over 3,000, and it is not a broad peak. So it is an OH, and it's really so important. It's an alcohol, okay? And we have a carbonyl group. Again, I guess, some of you might have thought, well, mate, could it be a carbon-carbon double bond? What I would say is, I think that is clearly around the 1700 mark, and also carbon-carbon double bond peaks tend to be a lot smaller. So if we just think about the four possible substances and we just draw their structures, and then we think about which parts of those structures would feature in an IR spectra, and with ethanoic acid it would be an OH acid and a carbonyl. For hydroxybutanone it would be an OH alcohol and a carbonyl. For propan-1-ol, just an alcohol, or OH, sorry, alcohol, and for propan-1-ol it would be an OH alcohol and a carbon-carbon double bond. So, okay, maybe there's an argument that I can understand. Maybe some of you might have gone for D, but I think you have to see now carbonyls are very clear, distinct peaks, and that is definitely, if anything, slightly above 1700. And so it has to be B. It has to be B. And then the very final question, which involved a proper sort of calculation. So we've got the heat released or energy released when 1 gram of ethanol undergoes complete combustion. What is the heat released by each molecule in joules? So an odd one, but we think about how many moles was in our 1 gram, and we can therefore work out what 1 mole of ethanol would release. And then once we have a mole, we know how many molecules are in a mole. It's Avogadro's constant. So we divide the value of kilojoules per mole by our Avogadro's number, and we get a value, that is 2, isn't it? We get 2.28 times 10 to the 18 joules. I'm not sure where you could have slipped up there, but anyway, yeah. And that's the final one. So I hope that's been useful. But again, if there's anything you're unsure about, get in touch with me and let me know.